Okay, we're just going to do this is going to be a little bit of a weird lecture. There are a few pieces that we want to sort of pull together in preparation for the next lecture. And just to cover some gaps. So we looked, right, so by the time you see this lecture, you'd have had the sort of first introduction to isomerism. You'd have had an isomerism 2 lecture. And then we're going to talk a little bit now about stereochemistry in small and medium rings. And then we're going to very briefly introduce SN chemistry. And then there will be some previous lectures that will come in and fill in that bit. So let's talk about stereochemistry. In small to medium rings. And we're basically looking at rings from size 3 to 6. Right? That's basically 3 to 6 atoms. So cyclopropanes, cyclobutanes, cyclopentanes, cyclohexanes. So what we want to do is, if you recall, we said that cyclopropane, which of course is the most strained of the rings, okay, can exist as if it were, it's not entirely flat, because there is a little bit of wiggle in the ring, but it's pretty much flat, so that the bond angles, you can't see them well here because it's so strained, but the bond angles are functionally 60 degrees. If you, and as a result of the lack of flexibility, there is no rotation that's allowed, and as a result, you can end up with scenarios where groups are stuck on one side of the ring or the other. So for example, I could have, yikes, that's not good. For example, I could have geometric isomerism arising in these rings even though there's no carbon-carbon double bond, because we never said geometric isomerism was unique, to alkenes. We just said it was true whenever there was restricted rotation. So to make the matter simple, if I had, for example, these white groups, they could end up, let's say, on adjacent carbons where they were cis to each other, and they could end up on adjacent carbons where they were trans to each other. Okay, so I can have the cis, yes, the cis 1, 2, okay, and I'll walk down here again. So this would be, and let's say these are chlorines or something, right? So this would be the cis 1,2-dichloro cyclopropane. This would be the trans 1,2-dichloro cyclopropane. They have very different chemical properties. This one, the dipoles are acting in opposite directions. So this is a non-polar compound. It would have a relatively low boiling point, relatively low melting point, relatively low aqueous solubility. This one is polar because I've got a dipole acting in this direction, one in that direction. So there's a net dipole acting this way. So this molecule has a higher melting point, a higher boiling point, higher surface tension, higher aqueous solubility than its counterpart. So how do we represent these molecules? Well, we could draw the cyclopropane on the board. And if I want to indicate it's cis, I just got to say they're on the same side. So I can indicate that with a wedge or a dash. I can indicate that with a wedge and say Cl, Cl. So that is the cis compound. To show the trans compound, I can show this, so Cl, Cl. So this is the cis compound, that is the trans compound. Okay, great. Is that where the story ends? Let's see. So we've talked about enantiomers and diastereomers. If I make the mirror image of the cis compound, what does that look like? Well, so here's my cis compound, and I'm going to build the mirror image. Okay, so here's the mirror image of the cis. Okay, so I've built, it's my object, here's my image. And I'm going to do that superposability test again. So if I do that, clearly they don't match. But I can turn it around, and that's exciting. I can turn it around, and I'll have, white and white, white and white, the blanks and blanks and everything. So they match. In other words, there is this molecule and its mirror image are superposable. In other words, this molecule is achiral. Okay, the molecule is achiral. And really, that's not too hard for me to picture, because if I look at this molecule, I've got a mirror plane that cuts right through the molecule. So, in other words, this is a mirror plane. And therefore the molecule, not surprisingly, is achiral. Which means, although it has the mirror image, as everybody does, mirror image and it are not superposable. What about the trans compound? And I'm particularly interested in the trans compound, because when I look at it, as I've drawn it here, there is no mirror plane in this species. And I know that the molecule is devoid of a mirror plane. That's one of the things we talked about last time. If the molecule is devoid of a mirror plane, then it should by definition be chiral. In other words, it and its mirror image are non-superposable. Okay, so here's my object. I'm making the trans compound. I'm going to make the mirror image. So I'm going to build it so that they are mirror images to each other. And so here's the object, here is the image. And I'm going to try the superposability test. So I'm going to do it, so that doesn't work here, right? So I'm going to turn it, so let's see, I'm going to try to turn it so that the white, some whites match. So these two whites match, but then these don't. I can turn it now so that this white matches, but then the other two don't. And I can do this from now until the cows come home, they will never match. So if I ask you, how many 1,2 dichlorocyclopropanes exist, you will tell me 3 of them. There is the cis compound, and there's only one of the cis, and then there is the trans compound. And the trans compound, there are 2 of them. There is the trans compound, and its mirror image. And these are non-superposable. So there's only one cis, but there are 2 trans compounds. Well, how are these trans compounds different? Well, they are non-superposable mirror images, so they're enantiomers of each other. And by the way, it doesn't matter whether I put the mirror here, or if I put the mirror here, for example. So if I put the mirror here, what I'll end up with is a compound that looks like this. So I have my Cl up here, far from the mirror, and then a Cl here. So if I call this compound A, and this is A prime, the enantiomer, well, this is also A prime. So these 2 things are the same. Okay? Or I could put the mirror here, put the mirror here. So how are these species different? Well, so again, as I said, they are enantiomers. And if I try to work a configuration, so I've got H behind the board here, and I've got H in front of the board here. So in terms of priority, this is first, second, third, with lowest priority behind the board. So this is 1, 2, 3, this is going this way, so this is the R site. And here my Cl is in the back of the board, or more correctly, inverted, my H is in front. So I'm going to read an invert. So this is first, second, third. So I'm going this way, which looks S, but really is R. Okay? So the mirror image of R should be S. The mirror image of R should be S. And let's just work it out really fast. So first, second, third, with the H behind the board. I'm going this way, first, second, third. So that actually is S. Here, first, second, third, with the H in front of the board, I'm going to read and invert. So 1, 2, 3, it looks R, but it really is S, because the H is out in front of the board. So I've got two different trans compounds. I've got the RR, and it's enantiomeric SS. This is meso, right? I've got a molecule that has two stereocenters, okay, which are symmetrically substituted, and they have opposite configurations. Because clearly, this is R, and if this one is the invert of this one, right? So if that one is R, this one must be S. Okay? So I've got the meso cis compound, which is the cis compound is the meso compound. And then I've got the trans compound, which exists as an enantiomeric pair. So there are three different 1,2-dichloro, or 1,2-dimethyl, or 1,2-dibutyryl, or 1,2-dihydroxy cyclopropanes. Well, that rule that we use in terms of looking for the mirror plane, looking for the sigma, if it's possible, is what we use to determine stereochemistry in the small to medium rings. And even though it strictly applies only to when the ring is flat, because it's flat in cyclopropane, it turns out that even though cyclobutane is not entirely flat, and cyclopentane is not flat because it puckers into the envelope, and cyclohexane is not flat because it twists into the rings or the bolts, that model of just assuming it's flat and looking for the mirror planes is exactly what we use to determine the stereochemistry. So although we know the cyclobutanes and the cyclohexanes are not flat, we treat them for these purposes as if they were. So if I ask you how many different 1, 2 dimethyl cyclobutanes there are, well, I can draw the cyclobutane like this. So clearly it'll be the cis and it'll be the trans. Okay? Oh, and let me just make a point. So since this is meso, it doesn't matter. Its mirror image. Let's say I put the mirror here. So I'm putting the mirror in front of the board. So I can draw this species. Cl, Cl, right? This compound and that compound are the same. They're the meso compound. Okay? So all I do is rotate this one this way, and it overlaps this one entirely, right? It superposes entirely. So how many different 1,2-dimethyl cyclobutanes are there? Well, remember the rings are rigid, so we do not have the flexibility to rotate from one species to the other. So if the methyls are on the same side, they're stuck. So I can have the cis, crikey, I can have the cis and the trans species. Okay, how many cises are there? Well, there's a plane of symmetry in this molecule. So this molecule is also meso, which means this and this are the same compound. So the cis is just one of them. Cis happens to be meso. Right? The cis is meso. So I've only got one of it. But the trans, right? The trans does not have a plane of symmetry, which means the mirror image of the trans, in other words, this species, right? These two are enantiomers of each other. One of them is going to be RR, one is going to be RX. So these are two different compounds. If I draw this one, and I ask you what's the relationship between A, B, and C? Well, A is related to B by a mirror. A is also related to C by a mirror. So A is the enantiomer of C. A is the enantiomer of B, which means B and C must be the same species. And let's just really quickly run through that. How would I know that? So one of the things I could do is to look for whether or not they're superposable. So let's do the simple thing. I can take this molecule and I'm going to turn it this way. Well, but let's look at configurations. So what's the configuration of this side? So this is so starting from here, I've got H, I've got CH3. I've got a carbon with 2 carbons on it. So this is first priority. Then I've got a carbon that has a carbon on it. So this would be second priority. Then I've got carbon with only H's. This is third priority. And then I've got the H, which is 4. So going from 1 to 2 to 3, going this way, right? This is going to be the R side. And I can actually tell what this one is, because if the mirror image of R would have been S. And since in this case the methyl is in front and here it's behind, it's not the mirror image, it's the opposite of the mirror image. So therefore if this is R, this also has to be R. Let's work it out to show, to make sure. So starting from here, this carbon, which has 2 carbons on it, will be first priority. Right, so this is the first priority from this side. This carbon has 1 carbon on it, so that's second priority. This methyl is a carbon with only H's, that's third priority. And of course the H is coming on the board. So I'm going to go 1, 2, 3, which looks S, but it really is R because the H is coming on the board. Right, so this is the RR species. Without thinking too hard, if these are mirror images, then this must be the S, this must be the SS compound. Yeah, so let me also, I'm just going to work out one as being S. So starting from here, first priority would be this carbon, so this would be first priority. Then this would be second priority. This would be third, and then the H is behind the board. So 1 to 2 to 3, I'm going this way, that's S. And you can work out this one as S as well. Okay. So that's one way of doing it. So this is the RR, that's the SS, so they're enantiomers. But enantiomers are also non-superposable mirror images. So if I take this molecule where the methyl is in front of the board, and I turn it around, the methyl is now behind the board. And therefore clearly, this one, if I turn it, it doesn't overlap here. Okay? They don't overlap. And even if I were to do this, if I were to turn it this way, they won't overlap. And you could build models to prove it. So these are non-superposable mirror images, they're enantiomers. Just very quickly on this one. I'm going to look at configurations here too. Starting from here, this is going to be first priority. This would be second. This would be third. And remember the H is in front of the board. So going from 1 to 2 to 3, I'm going that way, which looks R. So again, R and S. So going 1, 2, 3, it looks R, but the H is in front of the board, so this is S. Okay? And of course it is, the mirror image of R is going to be S. Right? And then lastly here, you guys can work that out. And what it will work out to be is SS. So that these two are the same. And these are enantiomers, and these are the same. Okay? So clearly then, there's one cis 1,2 dimethyl cyclobutane, and there are 2 different trans 1,2 dimethyls. What if it was the 1,3 dimethyls? Right? How many of those do I have? Well, again, I can have the cis and I can have trans. How many of them are there? Well, what I'm going to ask is there a plane of symmetry in the cis? Because that's what I'm looking for. And the answer is, yeah, there's a plane of symmetry here, right, that runs right through the molecule. That's it, something. Plane of symmetry that runs right through the molecule, which means that molecule and its mirror image, and I can draw the mirror image in lots of ways, right? I could imagine a mirror being here, and then drawing this species. Right, that's a mirror image, okay? Or I could put the mirror here and draw that species. Right? And this and that will be the same. But the point is, there's a mirror plane here, and therefore this species is achiral, and therefore it and its mirror image are the same. So there's one cis compound. Well, there's also a mirror plane here, which means there's also only one trans. So whether I draw that compound or I draw this compound, right, they're the same species. So while there are 3 1,2-dimethyl cyclobutanes, there are only 2 1,3-dimethyl cyclobutanes. And you can use this for 3-membered rings, 4-membered rings, 5-membered rings, 6-membered rings, which are called the small to medium rings. All you do is you look for a plane of symmetry. If there is a plane of symmetry, then the molecule is achiral, and it exists. Then it and its mirror image are the same species, or equivalent species. If there is no mirror plane, so if there is no mirror plane, then the species, what did I just say? So if there is a mirror plane, then it is achiral, and it and its mirror image are equivalent. If it is devoid of a mirror plane, if there's no mirror plane, then it is one of a pair of enantiomers. Okay? So when you're doing these questions, you're looking for both geometric isomerism, cis and trans, and then you investigate each geometric isomer for whether or not it is capable of enantiomerism. Okay? So when the question was asked how many different 1,2-dimethyls, I looked for geometric isomers, the cis and the trans. And then I examine each for the possibility of enantiomerism. I'm going to look for the mirror plane. If I have one, achiral, no enantiomers, one of these. I look for the mirror plane here. There is no mirror plane. If you're devoid of a mirror plane, you're going to exist as one of a pair of enantiomers. I could ask you, which of these compounds rotates plane polarized light? And the answer is this one does not, because it's achiral. Both of these do. And they do so in opposite directions. Okay? And if you work out their specific rotations, then the values have the same number but different signs. And that would have been covered in the previous lecture. While we're on rings, there is something that we have not done. So this is it for this topic. There is something that we also have to look at, which is how do we name bicyclics? So the nomenclature of bicyclics. So bicyclics, and these really are fused bicyclics. So if I have a bicyclic, let's pick a simple one. That species can also be drawn like this. So let's just make our way around this molecule. So a bicyclic essentially is 2 rings. So I can imagine this as having this ring and that ring. In other words, the ring on the left and the ring on the right. But there are two carbons that are common to both rings. The carbons common to both rings are called bridgehead carbons. So bridgehead carbons, I'm going to put asterisks on them. That's these two, or if you will, these two. And this is really, the one on the right is an attempt to draw a three-dimensional structure in two-dimensional space, which is always a challenge. And what that really is, I mean, you can tell it better from the one on your left, is a cyclohexane ring. So it's got 6 carbons. So 3, 4, 5, 6. It's a cyclohexane ring that is sort of pinched at carbons 1 and 4. So I'm going to take the cyclohexane ring, and I'm going to join the carbons of carbons 1, I'm going to join carbons 1 and 4 together by methylene group. So this, right, this structure has the 6-membered cyclohexane ring, right? And I'm connecting carbons 1 and 4 by a methylene group. And you can tell, so if I hold it this way, it looks at the structure on the left. If I hold it this way, it kind of looks at the structure on the right. Okay, so they're equivalent representations. I'm going to call these carbons, the one I'm holding, these are the bridgehead carbons. These are the ones connecting this 5-membered ring with that 5-membered ring. Now, the carbons that connect the bridgeheads are called the bridges. So I've got bridges, right? So I've got bridgehead carbons. I've got bridges. And I'll put the bridges, I'll put little zeros on the bridges. So these are the carbons in the bridges. So if you notice, I'll have 3 bridges, right? I'll have 3 bridges. In other words, the bridges are the paths between one bridgehead atom and the other. So that's one path, another path, another path, right? So these are my bridges. So for a bicyclic, you will always have 3 bridges. The way you name a bicyclic is sacrosanct. You call it bicyclo something dot something dot something something aim. And really it doesn't matter what groups are on it. That is the name you use. So it's bicyclo something dot something dot something aim. Okay, what are the blanks? The blanks in the square bracket indicate the lengths of the bridges in descending order of length. So if I look at this structure, my bridges have 1, 2 carbons, 1, 2 carbons, 1 carbon. So I would call this bicyclo 2, 2, 1. Those are the lengths of the bridges. This term is one of those prefixes that indicates the number of carbons in the structure. Only in the bicyclic, not the substituents in the bicyclic. So if I look at this, I've got, starting from here, I've got 1, 2, 3, 4, 5, 6, and 1 is 7 carbons. So I would call this bicyclo 221 heptate. Because hep is the prefix for 7. Now, there's another way of doing that. If you add the number of carbons in the square brackets, those are the number of carbons in the bridges. And all the carbons in the bicyclic are either bridges or bridgeheads. And there are always 2 bridgeheads. So if I sum the number in here, 2 and 2 is 4 and 1 is 5, I'm going to add 2 for the bridgeheads. And 5 and 2 is 7, so I get my head. What do I call this compound? And what do I call this compound? Some of those are that's highly strange, but let's let that go. So what do I call this compound? Well, where are my bridgeheads? Bridgehead 1, bridgehead 2. And what do I call it? I call it bicyclo 1, 2. I've got a 2-carbon bridge, a 2-carbon bridge, and a 2-carbon bridge. So it's bicyclo 2, 2, 2. 2 and 2 is 4 and 2 is 6, and 2 more for the bridgehead is 8. So this is bicyclo 2, 2, 2 octane. What do I call that one? Well, it's bicyclo. Here are my bridgeheads. Bicyclo 2, 1, 0. 2 and 3 is 1 and 2 is 5. Pentane. Right, so it's bicyclo 2, 1, 0 pentane. Right, because there's no atom that separates this bridgehead from that bridgehead. Right, so there's no carbon that separates them. So there are no atoms in the bridge. Okay, so that's all well and good for the basic carbon skeleton. But of course, these compounds often have substituents on them. So how do we name them if there are substituents? Well, essentially, the substituents are added to as a prefix to the name. And for example, if I have an OH here and let's say there's 2 methyls on that one. We number the atoms, the substituents on the longer bridge first. We number the longer bridge first. So if I'm numbering here, I'm going to call, and I always start off at the bridgehead carbons. So I want this to get a smaller number, so I'm going to go 1, 2, 3, 4, 5. Okay, so I number along the longer bridge first, or longest bridge first, longest. So 1, 2, 3, 4, 5. So I call this compound 2-hydroxy 5,5-dimethyl bicyclo 2,1,0-pentane. You notice, although normally when I have an OH group in a compound, I would call it like a pentanol, I never mess with the bicyclo 2,1,0-pentane unit. This takes the base name. Everything else becomes a substituent on the ring. If I have, let's say I have an OH here, and I have, let's say I've got 2 methyls on this one. Okay, what I will do is I will number it. So this is going to be, it's going to take my bicyclo, so the bicyclo 222 octane root. Now both of these rings, all of these bridges have the same number of carbons. So I'm going to number the more complicated bridge first, the one with the most substituents. So starting from here, and I always start at the bridgehead, I'm going to go 1, 2, because I've got 2 substituents. 3, 4, 5, 6, 7, 8. So I'm going to call this compound 2,2-dimethyl 6-hydroxy bicyclo 2,2,2-octane, and so on and so on and so on. So I want to number the longest bridge first. I always start with the bridgehead. Number the longest bridge first, and then if I have bridges of equal length, I will number the more complicated bridge before the less complicated bridge. Okay, and then the last thing we'll talk about, which will lead you directly into the lecture on SN1 and SN2, is just a brief introduction to what those terms mean. Because the lecture that I have, that I will post for you, makes mention of SN1 and SN2 being mentioned in class. Alright, so basically then we've talked about nucleophiles being electron-rich species. and electrifies being electron poor species. And we've done some curved arrow mechanisms and some syntheses to show how nucleophiles and electrophiles react. In fact, that reaction between nucleophiles and electrophiles forms, 80% of what happens of reactions in organic chemistry. Well, it turns out that if I have let's take a simple case of, say, chlorocyclopentane. If I treat that with, say, sodium cyanide, and let's say it's in some solvent like DMSO, what I end up with in this reaction is the corresponding nitrile and chloride. And that makes some sense. If I ask you for the mechanism or how that happens, you'll say, well, sodium cyanide is ionic, all sodium compounds are. So functionally, what this is Cn minus. And so what we're doing is a substitution reaction. We're having the nucleophile, so we're having the cyanide replace the chlorine. We're having Cn replace the chlorine. So that is a substitution reaction. And if you remember, we talked about the different classes of organic reactions. Substitution was one of those. So I'm going to ask, what character does the incoming group have? Is it a nucleophile? Is it an electrophile? Is it a free radical? And the answer is, it's nucleophilic, it's electron rich. And therefore, this I'm going to call a nucleophilic substitution reaction. And the way organic chemists designate those is as S, uppercase S, subscript uppercase N. So we say substitution nucleophilic. Why it's not NS versus SN? That's just convention. But it's important, the convention is uppercase S, subscript uppercase N. In other words, SN is wrong, SN is wrong, SN is wrong, SN is wrong. All of those are wrong. And in fact, these mean something very different in chemistry. So those are definitely not what you want to put. And some people do say they write their N's, their uppercase N's like that. That is not an uppercase N, it's a big lowercase n. Okay? And I'll say it again. Scientists communicate by symbols. This is the symbol, the accepted symbol for nucleophilic substitution reaction. This is right. Every other version is wrong. And if you mean for me to interpret Sn, this is what you write. If you write these things down, I'll just give you 0 for it because I don't know what those mean. That is not the accepted jargon of the science. So these are Sn reactions, and it turns out that Sn reactions can happen in some very different ways. So in one version of this reaction, cyanide may come in as a nucleophile and attack the electrophilic carbon. And again, why is that carbon an electrophile? Because it's attached to the electronegative chlorine, which is sucking electrons from it, creating a negative dipole on the Cl and a positive dipole on the carbon. So the cyanide can attack the carbon, and I can do a synchronous reaction in which I break the carbon-chlorine bond, I lose chloride, and I get my nitrile. In this reaction, which is one in which both the nucleophile and the electrophile are involved in that one step, this is up to and including the RDS, I would say this is what I call a bimolecular reaction. Right? Remember, two particles in the same step? So I would call this reaction SN2. It is nucleophilic substitution that is bimolecular. But there's an alternate mechanism. It turns out that this reaction can occur in a fashion in which the chloride might simply ionize. The haloalkane ionizes, chloride ion comes off, and that creates a carbocation. The carbocation can then attack or be attacked by the cyanide, and what I would get would be the corresponding nitride. And in this reaction, this step, the one in which we are breaking a bond, separating delta minus from delta plus, that's hard. That is a difficult step. Therefore, that's the RDS, and up to and including the RDS, one species, the haloalkane, is evolved. This is a unimolecular process. And so I would call this an SN1 reaction. So SN reactions come in two flavors. There is the bimolecular SN reaction, that's the SN2, and then there is a unimolecular reaction, which is the SN1. The unimolecular reaction goes via a carbocation, whereas the bimolecular reaction circumvents carbocation formation. Okay, so it turns out that there are some significant differences between the requirements for SN1 and SN2. There are significant differences between how you're able to direct the reaction, SN1 or SN2. There are significant differences as to the products of the reactions, of SN1 and SN2 reaction. In this case, it doesn't matter, right? This nitrile will have no difference from that nitrile. But I will tell you, if your molecule was chiral, then whether it goes SN1 or SN2 has a significant difference in what the products are. And so we'll pick up from there in the next lecture. This was just the introduction bit that we were missing. And in the lectures that follow, these topics will be developed in more detail. Okay, thank you.